Recitation 4. So, starting with sets. And what is a set exactly? Well, let's run through some examples of what makes a set well-defined. Now, the whole idea of a well-defined set, there are some specific rules that makes a set well-defined, but we'll worry about that in the future. Let's see what are some examples like that makes this kind of symbol true, where you like open the braces, then you put some objects in this set. What makes it a set? The collection of alphanumeric characters. So is that a set? Alphanumeric just means the numbers we know, 0, 1, 2 till 9, and then the alphabet A, B, C till Z, maybe capital letters. So is this a set? Yes. Just throw them in the bracelets, and there you go. That's a set. What about this? The collection of tall people. As it is right now, no, it's not a set, because what what's the character tall? What makes a person tall? And even the object itself, the people. Like, for example, if this was modified to say the collection of people in this class who are taller than X something, like some unit of measurement, then maybe, yeah, that would be considered a set. But as it is now, no, that's not a set. The collection of all real numbers X for which 2x minus 9 is 16. So the set of solutions for this equation. Well, let's see what the solution is. 16 plus 9, that's 25, over to 12.5. So here our set is just 12.5. Okay, why not? That's fine. We can have a set with just one element. That's okay. What about now? All integers x, for which 2x minus 9 is 16. So same equation, but now x has to be an integer. So the solution 12.5 doesn't work. Well, what happens now? So is this a set? Yes, it's technically still a set. It's just an empty set. And we refer to this as usually phi, or whatever you take in the main lecture. Here we're mostly going to be saying phi. Like an empty set is still a set. The collection of all good tennis players, exactly, that's a null set. So phi is a null set, an empty set, it simply doesn't have anything in it. The collection of all good tennis players. This is similar to kind of B, like what makes a tennis player good? So again, as it is right now, we can't make this set because, hey, you give me a tennis player, how do I know if I should throw him in this set or not? You have to give me something more specific, like did they win a certain number of matches, or they win a World Series, and so on. So let's dive into some of the operators we have on sets. So belong, subset, and equality. We're given 3 sets. Usually, U, it stands for your universal set. So you gotta have like the biggest set that you're gonna be working on. Kind of like when we were working with predicates, we had a domain, right? Like X belongs to the domain of students or whatever. This is sort of similar, like you need some big set to know where do these smaller sets come from. So U is the natural numbers, U for universal set. So 0, 1, 2, 3, and so on. We have A is 2, 4, 6, 8, 10. B is 1, 3, 6, 7, 8. Which of the following is true and which is false? Does 2 belong to A? So this symbol is for belong. Like, does this element belong in this set? Yes. I can see it right here. It's in the set, so it belongs to the set. True. Does 11 belong to B? No. There's no 11 here, so this is false. 4 does not belong to B. This is true. The element 4 is not in the set B. Does A belong to U? No. We might say yes, A is gonna be in U because U is everything, but this symbol belong is for elements. Like it's telling you, does the element A belong in the set U? No, it does not. So this is false. If it was A, is it subset in in U? Then yeah, it would be true. A is subset in U because all of the elements in A are also in U. And so this kind of like circular C, this is for subset. The line underneath it is when we say or equals. So usually we'd say A is subset in U or equals. If you know that it's not equal, like in this case, it's definitely not equal, you can just say it's subset. But the or equal in this case doesn't hurt. So I said that A does not belong to U, but is it possible that the set A belongs to some other set? Yes, that's fine. Let's say I want to create this set that has some other sets. Like it has the set N. It has the set R. Quotients has the set 1, 2, 3. And let's say also the set A. So I'll call this H. So in this scenario, yes, A does belong in H because there it is. I can see the set A. Here, the set A is just an element in the set H. So we need to differentiate between this stuff. Finally, does A equal the set of even numbers? No. Why simply say, hey, 12 does not belong to A? So it's definitely not equal to the even numbers. A is made up of some even numbers, but not all of them. Okay. If you want to say represent the even numbers, you'd simply say E equals X belongs to N such that X modulo 2 is 0. Or you can say simply X is even. So this is sort of how we build a set. X belongs to N. So we sort of built the main domain of X. It's an N. But we added such that, like an extra restriction, so either a slash or 2 dots, such that X modulo 2 is 0. So X is even. Any problems so far? Okay. If you have any problem, as usual, please ask me. What do we know about this? If U is letters of the alphabet, and A is this, B is this, C is this, what can be said about A, B, and C? So A is A, B, B, AC, B is C, B, AC. and C is just ABC. Well, they're all equal. A equals B equals C. Why? Well, there's two things we don't care about in sets, and that's yes, Reem, they're equivalent. So there's one thing that we don't care about in sets, and that's first of all, the order, like the arrangement doesn't matter. And no matter how many times you repeat a certain element, it also doesn't matter because we care about the uniqueness. So even though here we have A 4 times, it's as if you only wrote it once. So it's like A, B, C. And B here is just like B, A, C. So they're all equal because we don't care about the arrangement and we only care that the elements are unique. Venn diagrams. So another important idea of how we represent sets. So they're going to be asking us to identify the sets represented by each of the shaded areas. But just a moment before that, let's say we have the set A and B. We want to represent them in a Venn diagram. We make this big rectangle. And in the corner, you say U. Like this is everything. This is your universal set. It's everything where A and B live. Then we have the set A. We have the set B. We do this sort of intersection because they could have some elements in common. Then here there could be some elements that are only in A, some elements that are only in B. If you add another set, then it'll be like this. So there's an intersection that just has to do with A and B, A and C, C and B, and so on. You get the idea. You could say, hey, what if A and B don't have anything in common? Well, you could either write it like this, A alone, B alone, or just write them intersecting, and you can leave that part empty here. So let's identify these sets. First, A. Well, what is this shaded area? U minus B? Exactly. It's like everything other than B. So you can either say U minus B, or for example, B bar, like the complement of B, which means the exact same thing. It's just U minus B. Yeah. What about this one? So Reem is saying it's like A minus the intersection between A and B, which is correct, or we can just say, hey, A minus B, right? Both of them mean the same thing. Either you like remove the intersection, or simply, hey, remove everything. Same thing. Part C. So here it's kind of like I want the elements in A, the elements in B, but not both at the same time. So you're saying, is it A bar intersection with B bar? So this is B bar, A bar, yeah, no. Yeah, that looks fine. So A bar is like, so B bar is like in part A. It's everything other than B. No, actually that, I'm not sure about that. Yeah, that might not be right. So how I see it is I'm kind of trying to relate it to what we used to do with propositions. Does this remind you of anything in propositions? Like it's I either want A to be true or I want B to be true, but not both at the same time. Yes, it's like kind of like we're XORing A and B. Or it's like A minus B union with B minus A. So I want the elements of A, but not B. Sorry, I want the elements of A, yeah, and I want the elements of B, but not like the intersection of both of them together. Finally, D, obviously, it's the opposite. So it's bar of what we just wrote. So A XOR B, all of it bar. You can use De Morgan to make it less, to enter the bar. Okay, so that's Venn diagrams. Another idea, power sets. So let's say A is 1, 2, 3, 4. Write down the power set of A by listing its elements. What is the value of the size of P of A? We'll get to this second part in a bit, but when you say like 2 bars and a set, it's like the size of the set. So how many elements do I have in this set? But first, let's write some of the elements in the power set of A. To make it slightly easier, just assume it's made up of 1, 2, 3. So the power set of A, it's the sets that are subset in A, all of them. So starting off with just sets that are made up of one element, you have 1, 2, 3. Then the elements that are made up of that have a size 2, you have 1, 2, 1 and 3, 2 and 3. And finally, the set in itself is subset. So A is subset in A. So it does belong to its power set. 1, 2, 3. What's the size of P of A? Well, the size of the power set of any set, it's 2 power the size of that set. So the size of the power set of A is 2 power the size of A, which is 2 power 3. So we need to have 8 elements. But if you count them, we have 1, 2, 3, 4, 5, 6, 7. That's only 7 elements. Exactly, Reem, because the empty set is definitely included in the power set. Why? Again, the power set is just all the sets that are subset in A. Well, phi is subset in anything, so phi will be in every power set you ever make. Phi is subset in anything. Okay, moving on. Cartesian product. So another operator. Let's say we have these sets. X is this, Y is this. Write down the elements of x cross y. So we don't read this like x times y, it's x cross y. That's the Cartesian product. Y cross x. X squared is simply x cross x. How do we do the Cartesian products? Well, in the first scenario, we have x cross y. It's simply the couples where the first element is going to be in x and the second element is going to be in y. So it's in this scenario with x and y, they're all either going to start with A or they're going to start with C. There's no way it could start with B, for example, because B doesn't belong to A. There's no way it's going to end in C because C only belongs to X, and so on. So it's kind of like this. Let's say you have this set. You have these two sets. You put one sort of like a column, the other sort of like a row. You get all the possible elements. If they're the same element, like if you're doing A twice, just write it once like this, once like this. What could we say about two sets if A cross B equals B cross A? So if you have two sets, no matter how you cross them, it's gonna be the same. That could only mean that, hey, A equals B. So in this scenario, if no matter how you put A or B, they have to be equal if the Cartesian product is the same, because we know, obviously, the Cartesian product isn't commutative. So A cross B is different from B cross A unless A and B are the same. Simply just try to cross Y by X. Or actually, if you do part A and you do part B, you'll see obviously that you'll get different results. But what happens if we add another one? Like this is A cross B, this image. So what happens if I add another one, like A cross B cross C? Well, now it's just gonna be a tuple. So you're gonna get A from A, B from B, C from C. As a representation, it's like you're adding a third dimension. So right now, A cross B, it's just 2D. It's like flat on a paper. If you add another dimension, X, you can kind of imagine it's like a Rubik's Cube. So now it has a height, or it has a Z-axis. Okay, so that's an idea to think about. So time to actually try to solve something. Show that this thing is the same as this thing. Well, to prove equal or equivalence, we go two ways. Kind of like the implication. If you want to prove implication, you have to first prove this, then you have to prove this. So with the sets, first you have to prove the first subset, then the other one. I'll do the first. So how can we represent this set? Kind of like how I did with E, the even integers. This set is X such that X belongs to A, or X belongs to B and C, which is the same as X belongs to A, or X belongs to B, and X belongs to C. So this was I meant here the intersection between the set B and C. So now it's kind of looks like a proposition, right? Well, we don't know. This is the whole thing here. We're trying to prove the distributive law. We don't know if it's true. This distributive law. We don't know if it's true for sets, but we do know it's true for propositions. So we could say here, okay, X belongs to A or X belongs to B, and X belongs to A or it belongs to C. Finally, we just go back to the other thing, which is, yeah, so now just X belongs to A or B, and X belongs to A or C, and you're done. So this is A union C. Okay, so you simply downstairs you just write this is A union B, enter A union C. Okay, good enough for me. Try to do it in the other way around. So step one, build this as a set. What does it mean? And try to reach the other side. If you have a question on anything we've done so far, let me know. Yes, what about the subset symbol? What do you mean, do we only prove the left side? Because this is sort of the left side, this is sort of the right side. We have to prove both of them. I did the first one, you want to do the second. Yes, it's sort of going to be the same proof, because this is an easy example. Okay, so with that spoiler, it's actually, yeah, you can write the exact same proof as this. Because if you noticed, while I was solving this, I never really wrote subset, because I could have just wrote equivalence, because, hey, I'm not doing anything that's only going in one way. So this example was simple enough that I could have just wrote equivalence on each step, and I'm done. But in some examples, it might be more difficult, so you'd have to prove both the left and the right. So implication left, implication right, or subset, subset. Okay? And the assignments, I think you'll have plenty of those to do. Okay. One last idea about sets before we move on. So find the sets A and B such that these. So you have A minus B is this, B minus A is this, and the intersection is this. You want to find out what does A equal and what does B equal. Well, plenty of ways to do this. Let's write some of the definitions that we know. You have these three definitely, right? What does it mean that X belongs to A minus B? It's just that either X is in A, it means that X is in A and X is not in B, right? This is A minus B. X is in A, but not in B. B minus A is the opposite. X is in B, but not in A. Intersection, it's just in both of them. So to find out what's the elements in A, for example, you need both this and this, right? Exactly. It's A minus B plus the intersection. That's what you need. So we have to write to prove that that's actually what we need. So for every x, if x is in A minus B or x is in the intersection, what does that mean? Simply translate it into propositions first. So what we wrote in the given. Take x belongs to A in common. So it's x is in A and x is in B, or it's not in B. This is, let's not forget this stuff just because we did an exam. This is always going to be true. True and anything is just going to be that anything, so it's x is in A. So that's it. You proved the elements that are in A are either going to be in A minus B or the intersection. Easy enough. Similarly, you can say for B, if the elements are in B, then they're in B minus A or A enter B. Therefore, this is what A is, this is what B is. And it's kind of tedious to write all of this stuff, right? In order to prove this simple thing, that the elements in A are in A minus B or the intersection, we had to write all of this. Or, so this was your given, this was your conclusion. Or is there another way? Yes. Just use Venn diagrams, right? It could have been so much simpler. Hey, just draw the Venn diagram. This is A, this is B, and you have all the information. Just fill what A minus B is, what B minus A is, the intersection, and hey, there you go. That's your proof. That's enough proof. Okay. So that's some stuff about sets. One more. So take a couple of minutes to do, let me just check. Okay, after that it's functions. So take a couple of minutes, try to solve this, then we'll go over them. Because this is actually very important to differentiate what a set is, what an element is. This is very important for you to understand. So take a few minutes on this. We'll solve them, then we'll move on to functions. Okay, let's do this. If you didn't finish them, that's fine. Just focus with me so you can check if your answers was right. So, part A. Does the set xy belong to A? We mentioned this before. This is something that's false. X belongs to A. Y belongs to Y, or the set xy, exact theorem, it's subset in A. Is phi subset in A? Yes, that's true. Phi is subset in anything. Is the set phi, so is the set containing phi, is that subset in the power set of A? No, this is false. Because what does this mean? Or actually, I'm not sure if it's false or true. Let's see what this means and then we'll decide. This is saying every element in this set belongs to P of A. Well, what are the elements in this set? It's just phi. So this is like asking, does phi belong to the power set of A? So does phi belong to the power set of A? And yeah, it is there, right? This is just the empty set. It is in A. Sorry, it is in the power set of A. So true. Part D. The set containing the set Z is subset in P of A. So again, what does this mean? They're saying, does the set Z belong to the power set of A? Yes, it does. Since Z is an element of A, then the set Z, is the set containing Z, is going to belong in the power set of A. True. Part E. X and Z, do they belong to the power set of A? Yes. True. Or it's kind of like saying, does the set containing the set xz, is that subset in P of A? So the reverse of C and D, what's been going on. Is the empty set subset in A cross A? So part F, is the empty set subset in A cross A? Yes, without even thinking about what's on the right-hand side, because phi is always subset in anything. Yeah.
I have a question. We place phi in a set, we call it the set phi. It's the
Your
subset
voice
of
is.
our.
Can you repeat? Your voice isn't clear. I can't hear you, Reem. Maybe you can type your question.
Yes, sure.
Or you can talk now. I think it's better.
Is it better now?
Yeah, please ask your question.
Yeah, but I was asking about the phi as an element or as a set. Is a phi, we're considering it an element, we need to state that it belongs to a certain set.
Yeah.
Phi
Do you
is
mean part
placed
C?
as an element without a set. Yes, part B and part A.
Okay, so part B. Is phi subset in A? Yes, because they're simply saying, is the empty set? Are all the elements in the empty set also in A? Yes, because you have no elements here.
Okay, so we didn't treat it as an element here.
No, we read it here as a set. Same as part F. Both of them
Okay.
here are red
Okay.
essence.
All right. So we never have phi as an element alone.
Yes, we do, as in part C. When they asked us, is the set containing phi, is it subset in P of A? It's like they were asking us, does phi belong to P of A? So here phi was treated like an element.
Okay. Okay. So it's according to the context.
Exactly.
All right. Thank you.
Welcome. Okay, so we still have 3 more parts. G. Y and Z, do they belong to A cross A? No. Because, well, first of all, A cross A is going to be made up of elements. What are the elements of A cross A? They're couples. So A is just made up of elements, X, Y, blah, blah, blah. B is made up, the power set of A is made up of objects, sets. So X, Y, so on. So the elements in A are simply X, Y, so alphabets. The elements of P of A are sets. So depending on the set, the type of the element in that set will differentiate. Here it's a letter, here it's a set. In A cross A, it's simply a couple. So you have XY, like with brackets here, not bracelets. So XY, ZY, whatever, so on. So yeah, false for G and true for H, because yes, the couple Z, comma Z is an element in A cross A, because Z belongs to both of them. Finally, I is the couple. So this is kind of a big one. Is the couple phi and this set, does it belong to the cross of the power sets? Let's check. First of all, it's correct that they wrote couple belong to the cross. So this thing is right. We just now have to check, does phi belong to P of A? And does this thing belong to P of A? And in both of them, it's true. Because phi as an element, it does belong to P of A. And XYZ, which is simply A, it also does belong to P of A. So this is true. Okay? One last, just gonna throw this note. Phi does belong to P of A. This is true because, hey, when you write P of A, it's an element. It's right there as an element. So phi does belong. When we're asking, is phi subset in P of A? It's also true. Here we're asking, are all the elements in phi, are they also in the power set of A? Yes, because can you find an element here that's not here? No, because you don't have any elements to begin with. So they're definitely all there. What do you mean? Why didn't we place it in a curly bracket? You mean like this? So the set containing phi, is it subset in P of A? You can write it. That just means something else. That's true. The third sentence I wrote here, it's the exact same thing as the first one. In the first one, I'm saying phi belongs to P of A. In the third one, I'm saying the set containing phi is its subset in P of A, which means that this element doesn't belong here. So all three of these are true. The only thing left to check, it's right here. It's part C. The only thing left is the set containing phi, is that subset in P of A? Oh no, actually that's right here. So the only thing left to say is the set containing phi. Does this belong to P of A? So this is the last combination, and this one is false because this whole thing as an element, it's not in P of A. Okay, so that's that. Okay, we're going to be moving on to functions. If you have any questions that have to do with sets, please ask me now. I think it's going to take me around 20 to 30 minutes to finish what I have to say about functions. So if you, at any point you need to leave, that's fine. I'll upload this when I can. So yeah, around this to finish functions. And then on my own time, I'm going to record some thoughts about cardinality and upload them. And as always, you can ask me if you have anything on that. Otherwise, if you're gonna stay with me, strap yourself in because we have a couple of nice big ideas to talk about. So I've mentioned functions slightly before when we were talking about predicates. I said a function f is simply a mapping from one set to another. It's like it takes the element. So if x belongs to A, it maps it to an element f of x such that f of x belongs to B. So in predicates, what I was talking about, like for example, let's say P is the normal predicates symbol we know. Your set could have been the students, so like your domain. And our mapping was always the set true false, right? Because a predicate can either be true or it can be false. So before we were always saying, hey, if X is a student, then P of X is either going to be mapped to true or it's going to be mapped to false, depending on the truth value of that statement. Like X has a driver's license, depending on the student. Does he really have it, or she? Do they really have a driver's license? If yes, true, else false, so on. So that's functions. It takes you from one set to the other. But one important idea that what makes a function, every element in the left set has to be mapped to the right set. Every element in the left has to be mapped to the right. So let me clear that. So if you have your set here, students, and here we have my true and my false. All the students here, they have to have some mapping that takes them to either true or false. It's fine if this thing doesn't have someone on the left side. So if all of these students, if all of them were true, and none of the students were pointing to false, that's fine. It's okay if this set doesn't have something here pointing to it. But it's not okay if you have a student here that doesn't point anything over there. It's no longer a function. So that's the only rule about functions. Everything here has to be mapped to some element in the other sets. And with that only rule about functions, let's add some, let's we say some properties. So injective, or we can say 1, 2, 1. Surjective, and bijective, which simply means both injective and surjective at the same time. Or we can say 1 to 1 correspondence. So what do all of these mean? Well, let's see what injective means first. So this image is about injective. Simply means every element here has a distinct mapping. So 1 points to B, 2 points to B, 3 points to A. They're all distinct. So for every x1, x2 belongs to x, if x1 is different than x2, that means the mapping is also different. Okay? It's that simple. Each element in X has a distinct mapping in Y. What about surjective? Simply means each image here. So we also call Y, you can call it the image. Every single element has a pre-image. So you remember the rule I said, or when I was saying here false, it's okay if false doesn't have anything pointing to it. It's still okay. It does mean you're a function, but a surjective function, it does, each element in Y will have something pointing to it from X. Finally, when you combine both injective and surjective together, you get a bijection. You simply get this. 1-to-1 correspondence. Each element here has exactly one element over here. They're all distinct, and you don't have any element in Y that's not pointing to anything, that doesn't have something pointing to it. Last example. This is neither injective nor surjective. Why is it not injective? Here, you have 1 and 2. They're different, but they're pointing to the same image, which is D. So x1 is different than x2, but the images are equal. That's why it's not injective. They have to be different. Why is it not surjective? Hey, you have A and B, they don't have anything pointing to it. Why is it a function? 1, 2, 3, they all have images. Moving on. I'm mostly going to be solving these exercises on my own. There's an idea at the end. I'd like it if you could solve it. But for this one, let's try to think together. Prove that a strictly increasing function from R to itself is 1-to-1. So if we try to relate this like what we took in school, first of all, they're saying from R to itself. So R to itself, it's like R squared. It's simply R cross R. Kind of like in school when you have X, Y, drawing it on a board. Okay. So this mapping is simply doing what? It takes your X and it gives you f of X, which is going to be Y. So for example, this one, it's X1. It gets mapped to something here, f of X. Anywho, prove that a strictly increasing function from R to itself is 1-to-1. So if I draw this, it's strictly increasing. Does that mean because it's strictly increasing, it's injective? Okay, let me answer this question. 3 and 4 in figure 3 point to the one element though. Yes, that's okay, Because in this image, in image 3, we only care that the function is surjective. So all these, D, B, and C, they all have pre-images pointing at them. The fact that both 3 and 4 point to C, this simply means that this is not injective. But we only care that it is surjective in this case, but it's not injective. Okay? Sorry, I missed that question. Okay. We're gonna prove this using contradiction. So this is your given. If you're given a strictly increasing function, does that imply it's one-to-one? So is it injective? And if you remember contradiction, this means we're gonna assume that it's not injective. What's my given? For every x, y belongs. These are just variable names. You can call them x1, x2, xy, whatever you want. For every xy that belongs to R, if x and y are different, then that means f of x is different from f of y. We're just writing the, what does it mean? Okay, never mind. I made a mistake here. This is the definition of injective. What does it mean to be strictly increasing? My bad. For every xy in R, if x is strictly less than y, then that means f of x is strictly less than f of y. Okay? What does it mean to be strictly increasing? If you have here x, and this is y, x is strictly less than y, then definitely f of x is gonna be less than f of y. That's the given. Now we're gonna assume that it's not injective. What does that mean? You have x is different than y, and f of x equals f of y, right? This is when you're not injective. You have two different elements in your preset or pre-image, but their image is the same. Well, what does it mean that x is different from y? Two cases. Either x is less than y, or y is less than x. Without loss of generality, let's just assume it's this. So if x is less than y, well, according to your given, it should be f of x is less than f of y, but you assumed that they're equal, so contradiction. They have to be different. Take a second to mesmerize this. So you're given it's increasing. That means, hey, x less than y, f of x is less than f of y. You assumed it's not injective, which means x is different from y and their images are equal. Well, if x is different than y, then one has to be less than the other. Assume x is less than y. You get a contradiction because if x is less than y, according to your given, the image of x has to be less than the image of y. But here you're saying they're equal, so contradiction. You simply write it like this. I'll read it one last time just in case. This is your mapping from R to R. It's strictly increasing. So if x is less than y, f of x is less than f of y. Suppose by contradiction, the images are the same, but the pre-images are not. One of them has to be less than the other. Without loss of generality, x less than y, then you should get this. But contradiction, because of your assumption here. Okay, hopefully that was clear. Find an example of an increasing function from R to R that is not one-to-one. Can anybody think of that, of an example like that? Is it exponential? Exponential? Well, what's exponential? It's this, right? Starts from 1 and keeps increasing. So no, I think exponential is a strictly increasing function, so it's not that. 0, 0, we're only so you're saying 0, 0 gives you, so an exponential e of x. That's another thing you're saying. Yes, so only the point 0, 0, yeah, that's not a function. So you want an increasing function that's not one-to-one. What does that mean that it's not one-to-one? At some point, you're gonna have two different x's with the same y, or with the same image. So if I want to draw this, let's say I have here x1 and I have here x2. I want them to have the same image. But I also want my function to be increasing. So done. That's an example. Right? This is an increasing function. Remember, it's not saying strictly increasing. You have to be careful with the words. It's just saying increasing function. And this, yes, is an increasing function. It was constant here, but it wasn't decreasing. It's still increasing. So that's an example. Or the function f of x equals 2. Simply 1, 2. This constant function, which is just a horizontal line, it's increasing, right? Remember, not strictly increasing. This is just increasing. And hey, every image is the same. x1, x2, x100. They all have the same image, so it's definitely not going to be one-to-one. Parabola. Would a parabola work? What do you think? The problem with parabola, it sometimes decreases, right? So you have this. It's sometimes it's decreasing before it increases. Here they want it increasing at all time. So it does. So a parabola is definitely not one-to-one because you have a bunch of x's that share the same image, but it's not always increasing. Okay. Good guess though. Okay. we come to the last exercise, the last idea of today, and it has to do with round. So f round g. Well, take a deep breath. It's not hard, but I need you to really focus with me here. So just a quick description, f round g of x, this is simply f of g of x. We'll see what that means in a second, but it's kind of like first you do the mapping using g, then the result of that you do the mapping using f. So what's part A asking? Show that if both f and g are one-to-one functions, then f round g is also one-to-one. Okay, but what is g? It's a function from A to B. So let's draw that. I have the set A, set B, and g is just the mapping from here to here. F is a function from B to C. I'll add C. F is from B to C. So again, what's f round g? First, you have an element in x. You have to use g of x first, so it gets mapped g of x. Then that element, it gets mapped f of g of x, which is f round g of x. Okay, so this whole thing from A to C, it's f round g of x. So we're given that f and g are one-to-one functions. So they're injective. So there's no two elements here that point to the same element here. And there's no two elements here that point to the same element here. It's injective. Show that if f and g are one-to-one, then f round g is also one-to-one. Let's try to just prove the definition. So we're going to say, hey, let x and y belong to A, and x is different from y. If we can reach that f round g of x is different from f round g of y, we're done. It's over. That's the definition of one-to-one. So let's do that. And it also works because we assumed we simply said let x and y belong to A. So they're any two arbitrary elements. So this is x, this is y. Well, step one, we know that g is one-to-one. So g of x is different from g of y. These are two different elements. Simply because g is injective. G is one-to-one. X and y are different, so their images using g is different. But now, using the same logic, g of x is different from g of y, so their images using f is also going to be different. Because f is injective. And done. That's it. We have to state it formally, of course, but that's the idea. Yes, this is simply direct proof. We're given this, we want to reach this conclusion. Let's see how it's written. Assume both f and g are 1 to 1. We need to show that f round g is 1 to 1. Let x and y, two distinct elements of A. We want to prove this. Their images using f round g is also different. First, g is 1 to 1. Then by definition, g of x is different than g of y. Now, g of x and g of y, they're in B and they're different. So again, since f is 1 to 1, you get this. So it's pretty straightforward when you think about it. Okay. So this is, again, this is the last idea for today. So I want you to try and do B. If you didn't get part A, please ask me now. Okay. Try to do the same thing for part B. Like draw the set A, B, C. In part B, they're asking for surjective. So you're given that F and G, they're both surjective, they're both onto. You want to prove that the round is also onto. So by definition, you're gonna say, hey, let Z belong to C. So let Z be some element in C. You have to prove that there exists some element here such that F round G of E equals Z. So it's in reverse. You're gonna start from C and you wanna reach A. Should you do it by contradiction? I think direct proof also works in this case. If you can find a way to do it in contradiction, why not? Okay, so take a few minutes to do this. And again, please ask me if there's anything not clear. I think, so you're saying, can we say that X and Z aren't equal, but their images are equal? So pointing to F and then you talk about the round. I think here you're mixing both definitions together. Let me just draw it first. So you have A, B. I'm not gonna solve it just yet. So if you're thinking, keep thinking, keep working. C. This is G, and this is F. The definition of surjective, it simply says for any element in C. So for any Z in C, there exists X in A. So here I have an X such that F round G of X equals Z. That's all you have. That's what you want to prove. So you have this as given, like hey, just Z belongs to C. You want to prove that you can find an X in A such that F round G of X is A. There's no X. First of all, X has no relation with Z because they're both in different sets. But if you were saying X and Z are both in A and saying they're different, That's also not necessary because now we're talking about injectivity or injection. So this is all you care about. You have some element in C. You want to try to find X in A. The reason I skipped B because F round G is a mapping from A to C. That's why I want to try to find X in A and not in B, for example. Almost. You're saying surjective means it should have a pre-image in B, right? No, no, not necessarily. Let me write it somewhere. So what does it mean to be surjective? Let's say you have a mapping. It could be called anything. So a mapping H from the set X, big X, to the set Y. If H is surjective, then that means for any element in Y, Z, it's gonna have an element in X. So again, this is my X. This is my Y. Any element in my image set in my Y is gonna have a pre-image. So H is from X to Y. So any Z in Y has to have a small x in big X. Okay, here F round G, it's from A all the way to C. So any element in C has to have a pre-image in A. Like you can imagine B doesn't exist because F round G, it doesn't see B, it's working from A to C. Okay. So you have to be careful what's your left-hand set and your right-hand set. What's your pre-image and what's your image. Almost. I'll explain. You're partially right. I'll explain which parts you're right in. But let's give a couple of more minutes if anybody's trying to solve. Okay, let's do this. Please try to focus with me. Okay. So before, when I said this was your given and you want to reach this, it's more of like this is your premise. You have a lot more given than just this. You also have that F and G, they're both surjective. So just first explaining again what surjective means. So if F is surjective, right? So if you have here A, then definitely you're gonna have here an image, let's say B. Actually, let me call this C. So if you have C, here a small c, then you're gonna have a B here such that F of B equals C. Same thing, this small b, since B is surjective, or a different element, let's say D. Since G is surjective and G is working from A to B, then D is gonna have something here that points to it. So Reem, when you were saying surjective means it should have a pre-image in B, if you were talking about F, you are correct. Any element here, using F, it's gonna have a pre-image in B. But if you were talking about F round G, that's not correct, because F round G works from A all the way to C. So any element in C, according to the eyes of F round G, it should have a pre-image in A. It will do a stop at B, but F round G doesn't care about that. It only sees A and C. Let's solve this. So, for every Z belongs to C, well, hey, F is what? It's surjective. So you can have here some element Y such that F of Y equals Z. Y is an element in B. Using G, since it's surjective, it's going to have some element in A. Let's call it X, such that F of X equals Y. So Z equals F of Y, and Y is F of X. So simply write instead of Y F of X, you get Z is, sorry, this isn't F of X. My bad, this is G of X. The mapping from A to B, it's using G. So Z is going to equal F of Y, and Y is G of X. So Z equals F of G of X, which is F round of G of X. Done. You did it. You started with some random element in C, and you were able to reach that there's an element X in A. Let's see how they wrote it. Assume both F and G are onto. We need to show that F round G is onto. If Z is any element of C, so let Z belong to C, then there is some element X in A such that F round G of X is Z. This is what we want to prove. Since F is onto, we can find an element Y in B such that this. This is the definition of surjective for F, which works from B to C. Then, since G is also surjective and Y is in B, we can conclude that there is an element in A such that G of X is Y. This is again, since this is G working from A to B. G of X. And this thing here, this was F, also working from B to C. Z was here. We were able to find y here such that f of y equals e. And that's it. We just use the definition. We just, using direct proof, we assume there's some z in C. We reached an x in A. So that's it. Whew. If you have any questions, please let me know. I'll upload something that has to do with cardinality so you can practice for your assignment. You're welcome. Okay, great. Okay, I'm gonna leave the meeting open for a couple of minutes just in case anybody wants to ask. Otherwise, we're done.